During the next few minutes, what I am going to do is to introduce and define those physical quantities that are necessary to define as accurately as possible the different wave motions that we observe in nature around us. Among the characteristic quantities, those physical quantities that I am going to need to characterize well the wave motion, I am going to introduce the vocabulary because I am going to analyze and talk about the wavefront, the ray, the amplitude, the wavelength, the frequency, the period, the wave number, and we are going to see how to calculate the propagation speed of that energy that accompanies the wave motion. If we stop to analyze the different characteristics that we have of wave movements, then simply by the geometry we see that, for example, we have here a very characteristic geometry in what would be the disturbances that are being caused on the surface of a fluid when it is disturbed. On the other hand, when analyzing the electric and magnetic fields that define an electromagnetic wave, we see that they also have a very peculiar characteristic and that we would already be a little bit able to imagine the sine waves that are forming those fields and defining those electromagnetic fields. In this case also, because the perturbations produced in a spring, I see that those parts of the spring go from a maximum displacement to the right to a displacement to the left, that is to say, an oscillation with respect to an equilibrium position. All these parameters we are going to be able to summarize. Summarizing them a little bit by making them together with the definition of the different physical quantities that I want to deal with. Here we have seen how the perturbation in the fluid caused by J, immediately we observe some patterns that are familiar to all of us since we have all played this game at some time. Let's start by defining what the wavefront associated with wave motion and lightning is. Well, the wavefront is defined as the geometric locus of points that are in the same phase of their oscillation. And the ray would be lines perpendicular to the wavefronts. For example, if I analyze, in this case, a surface of a liquid where I have a disturbing source that could be the impact of droplets that are falling and are producing each time an impact, what are being generated in a particular line of the space of that surface of the fluid? Well, they are generating what we call in colloquial language waves, and it is like a sinusoid that is being defined on that surface of the fluid. Well, another way would be, in that case, I want to analyze already by when what I have is a deformation, but it does not occur with respect to a particular point, but in a whole strip, we see then that this pattern is also formed as a sinusoidal pattern as well. Very well. In this case, we see that those points that meet with the same phase would be points that form lines. It would then have the definition of a linear wavefront. On the other hand, in what I mentioned before, what you would have in the impact of water droplets on the surface of a liquid, you would have wavefronts, because in this case, they would be cylindrical with respect to the point of the perturbation. And you could also have spherical wavefronts, as for example represented by the waves of an earthquake or an explosion. At a certain point, they would be spherical concentric waves. What would be the rays? Rays are lines perpendicular to the wavefronts. What do I mean? Well, for example, in each direction of the wavefront, if I draw perpendicular lines, in the case of circular waves, as in this case, the rays would have this direction, in this case, perpendicular direction to the different wavefronts. What would the rays show me? Well, the direction of propagation of the wave motion. More physical magnitudes that interest me I have here. The example for the case of seismic waves. If an earthquake is occurring in a certain point of the earth, in this case we have then what would be the graphic documentation of an earthquake that occurred in Italy. We have before the earthquake, as we had the structure of strata, after the earthquake as it occurs here, the area where the displacement has occurred, and here a representation of how the seismic waves have been propagating along the entire terrain. We would have then the wavefronts clearly differentiated, and the rays would show me the direction of how this earthquake is propagating in different points of the globe. Well, more definitions. If we analyze, for example, how the waves are propagating in this simulation here, we see that I have a sinusoidal pattern. Well, I could represent that pattern by a function as I have here sine, simply with an image like the one I have represented, a sine function with a very well-defined argument. Well, the amplitude would correspond to the maximum disturbance that is occurring in the medium. It would have, at this point, for this representation, the eye would play the role now of the maximum altitude that the water droplets are acquiring. If it is the surface of a liquid, water in this case, the maximum amplitude and the minimum amplitude, the maximum height and the minimum height. In this case, the perturbation, what would its dimensions be? Well, in the international system, it would have dimensions of a meter, and the amplitude, obviously also because it would represent the maximum deformation that is occurring in that case, the maximum vibration, and the wavelength. Well, the wavelength corresponds to the minimum distance between 2 points of the medium that are in the same state of vibration, in the same state or the same phase of oscillation. In the case of the international system, that wavelength, represented by the Greek letter lambda, is going to be measured in meters. Here I have a periodicity in space, you might say, but it turns out that that same periodicity, what I do now is to look at this simulation and look at a particular point on that surface. It turns out that that point, I try to establish it with the pointer. It turns out that I am also seeing that at that point, the water droplets are oscillating between a maximum and a minimum height. If I pick up that variation, in this case not as a function of space but as a function of time, I also see that the oscillation goes between a maximum amplitude and a minimum amplitude, and in that case I will define the period for a time scale as the time it takes for a point in the medium, in this case the surface, a droplet on the surface of the liquid, to be in the same phase of its oscillation. Its symbol in the international system we work with would be the capital T, and it is measured in seconds. And the inverse of the period defines the other physical quantity, the frequency, which in the international system is measured in hertz and corresponds to the number of periods that I am going to have in 1 second. More physical quantities that I will need to characterize, well, the different wave motions. Well, I am going to talk about the wave number, which is related to the wavelength, or what is the same as the periodicity in space of a wave motion, which is represented by the letter K. According to the bibliography, or K or kappa, the Greek letter kappa, and is defined as the number of times a wave vibrates in the unit of distance, in 1 meter. It could be defined directly as the inverse of the wavelength, but let's see how there are other definitions for this same wave number. And the speed of propagation then, what it will give me is the speed with which the energy that is transported by the wave motion is propagating, and that speed of propagation has to do with space and time. In our case, to determine it for a wave motion, it is going to be determined by the wavelength and by the period of this form that we have here. If we now look at the electromagnetic spectrum, we can see how these physical quantities that we are introducing have an immediate application and already allow us to characterize when I am talking, for example, about radio waves. In what range of frequencies I'm going to talk, in what range of wavelengths I'm going to talk when I talk about the scale of microwaves or infrared or gamma rays. Later, in other lessons, I will go into these characterizations, but I see how these definitions that I am giving will allow me to make a more direct and more exact study of the different wave motions. Therefore, by way of summary, we have already seen and we have introduced a lot of new vocabulary, where we have to become familiar with it because we need it to carry out an exact study of the different waves. And let's review what magnitudes have we introduced so far. The wavefront, what are the rays? That are defined from that wavefront. It shows me its direction, amplitude, wavelengths, frequency, period, propagation speed, and wave number. Thank you.